Hello there, and welcome to the Sleepy Science Society. I'm so glad you found your way here tonight. Maybe you've had a long day, or maybe you're the kind of a person who likes drifting off to the gentle rhythm of cosmic mysteries, rather than counting backward from 100. Either way, you're in the right place. Tonight's journey is all about one of the most fundamental constants in our universe. A number that defines not just how fast light travels, but the very structure of space, time, and reality itself. The speed of light. It's a phrase we hear often, but beneath those simple words lies a story of human curiosity, brilliant insights, revolutionary physics, and profound philosophical implications about the nature of existence. And before we begin this journey together, if these gentle explorations help you unwind at the end of your day, consider liking this video and subscribing to the channel. It helps others find their way here too, one curious mind at a time. Now, let your breathing slow, your thoughts settle, and let's begin. Light is something we take for granted. It fills our days, illuminates our world, lets us see the faces of people we love and the beauty of a sunset painting the sky. We flip a switch and rooms flood with brightness. We look up at night and see starlight that has traveled unimaginable distances to reach our eyes. But for most of human history, no one really understood what light was or how it moved. Was it instantaneous, appearing everywhere at once? Did it flow like water through invisible channels? Or did it travel at some specific speed, racing through space at a pace we might someday measure? These questions puzzled the greatest minds for thousands of years, and the answers, when they finally came, would reshape our entire understanding of the universe. The ancient philosophers had strong opinions about light, even without the tools to test their ideas rigorously. Aristotle, whose influence stretched across centuries, believed that light moved instantaneously. In his view, light was not something that traveled, but rather a state of being, a quality of transparency that spread through a medium without any delay. It was there or it wasn't, with nothing in between. This made intuitive sense in many ways. After all, when you light a candle in a dark room, doesn't the entire room seem to brighten at once? When the sun rises, doesn't the world transform from darkness to light in what feels like an instant? For someone living in ancient Greece, without telescopes or precision instruments, the idea of instantaneous light seemed perfectly reasonable. And because Aristotle's word carried such weight in intellectual circles, this view persisted for a very long time. But not everyone agreed. Some thinkers suspected there might be more to the story. The question was tantalizing because it touched on something deeper than just light itself. It was about the nature of the universe. If light took time to travel, that meant there were limits to how quickly one place could influence another. It meant that what we see might not be what exists at this very moment, but rather a glimpse of the past. These implications were profound, even if the technology to explore them didn't exist yet. Still, the seed of doubt had been planted. Maybe light wasn't instantaneous after all. Maybe it moved, traveled, journeyed from one place to another at some finite speed. But how could anyone possibly measure something that seemed so impossibly fast? The first serious attempt to measure the speed of light came from an Italian scientist whose name you probably know well. Galileo Galilei, Already famous for his telescopic discoveries and his battles with the Church over the nature of the cosmos, turned his attention to this puzzle in the early 17th century. His approach was beautifully simple in concept, though challenging in execution. Galileo devised an experiment involving two people standing on distant hilltops, each holding a lantern covered by a shutter. The plan was straightforward. One person would uncover their lantern, sending light toward their partner. As soon as the second person saw that flash of light, they would uncover their own lantern in response. The first person would then measure the time between uncovering their lantern and seeing the return signal. If light traveled instantaneously, there would be no delay beyond human reaction time. But if light had a finite speed, there should be a measurable gap, a tiny pause that would reveal light's velocity. Galileo and his assistant tried this experiment, probably on hillsides around Florence, with lanterns and shutters and careful timing. But the result was frustratingly inconclusive. Galileo could detect no delay beyond what seemed to be normal human reaction time. He concluded, quite correctly, that if light did have a finite speed, it was far too fast to measure with the tools and methods available to him. In his own words, he noted that if light's speed wasn't infinite, it was at least extraordinarily rapid. This was an important realization. Galileo had demonstrated that measuring the speed of light would require either much greater distances or much more precise timing than could be achieved with lanterns on neighboring hills. The question remained open, but Galileo had taken a crucial first step by showing that the problem was tractable in principle, even if not in practice with 17th century technology. The decades that followed saw other attempts and continued debate. The French philosopher René Descartes, wielding enormous intellectual influence in his time, argued forcefully that light must travel instantaneously. In his mechanical philosophy of the universe, light was a kind of pressure transmitted through an invisible medium, and such pressure, he reasoned, would propagate instantly. This wasn't just an academic position for Descartes. His entire physical theory, his explanation of planetary, motion, and natural phenomena rested on the assumption of instantaneous light. If light took time to travel, it would undermine much of his carefully constructed system. So, Descartes defended instantaneous light with the passion of someone whose worldview depended on it. And because Descartes was Descartes, his opinion carried weight. Many natural philosophers sided with him, and the debate continued with no clear resolution in sight. But then, in the year 1676, everything changed. A Danish astronomer working at the Paris Observatory made an observation so elegant, so unexpected, that it would finally settle the question and open up entirely new realms of understanding. His name was Ole Rømer, and he wasn't even looking for the speed of light when he found it. Rømer was conducting a series of careful observations of Jupiter's moons, particularly Io, the innermost of the 4 large satellites that Galileo had discovered decades earlier. These moons were more than just interesting celestial objects. They were potentially useful. Galileo himself had suggested that by timing the eclipses of these moons as they passed into Jupiter's shadow, astronomers could create a kind of universal clock, a celestial timepiece that could be used anywhere on Earth to determine longitude and make better maps. So Rømer was dutifully recording when Io disappeared behind Jupiter and when it re-emerged, compiling tables of these eclipses with meticulous care. But something strange kept happening. The eclipses didn't occur quite when his calculations predicted. When Earth was on the same side of the Sun as Jupiter, moving closer to the giant planet, the eclipses happened slightly earlier than expected. And when Earth was on the opposite side of the Sun, moving away from Jupiter, the eclipses were delayed, occurring later than they should. At first, this might have seemed like an error in the calculations. Perhaps some mistake in understanding Io's orbit, or some peculiarity in how Jupiter's gravity affected its moon. But Rømer realized something remarkable. The pattern was too consistent, too regular. The delays accumulated in one direction and then reversed as Earth's motion changed. This suggested that the discrepancy had nothing to do with Io itself. Instead, it had everything to do with the changing distance between Earth and Jupiter. Rømer's insight was brilliant. He proposed that light from Jupiter and its moons took time to reach Earth. When Earth was closer to Jupiter, that light had a shorter distance to travel, so the eclipses appeared to happen sooner. When Earth was farther away, light had a longer journey, and the eclipses appeared delayed. The difference in timing wasn't about Io's actual orbit, which remained perfectly regular. It was about how long light took to traverse the changing distance between the two planets. This was the key. By measuring the time delay and knowing the diameter of Earth's orbit around the Sun, Rømer could calculate how fast light traveled. It was an indirect measurement, relying on planetary motions rather than lanterns on hillsides. But it was ingenious precisely because it used the vast distances of the solar system as a natural laboratory. Rømer estimated that light took about 22 minutes to cross a distance equal to the diameter of Earth's orbit. This number was actually too high. The correct value is closer to 16.5 minutes, but that wasn't Rømer's fault. The size of Earth's orbit wasn't precisely known at the time, and the observations themselves had inherent limitations. Still, the principle was sound. A Dutch scientist named Christian Huygens took Rømer's time measurement and combined it with the best available estimate for Earth's orbital diameter. When Huygens did the arithmetic, he arrived at a speed of about 131,000 miles per second, or roughly 210,000 kilometers per second. This was lower than the true value of about 186,000 miles per second, but it was in the right ballpark. For the first time in human history, light had been measured. It wasn't instantaneous. It traveled at a finite, comprehensible speed. The reaction to Rømer's discovery was mixed. Some scientists, including the brilliant astronomer Christian Huygens and the English polymath Edmund Halley, recognized its importance immediately. Here was proof that light propagated through space at a definite velocity. But others remained skeptical. Giovanni Domenico Cassini, Rømer's own director at the Paris Observatory, never fully accepted the idea. Cassini pointed out that the other 3 Galilean moons didn't show the same timing anomalies as clearly, and there were other irregularities in the eclipse observations that Rømer's theory didn't explain. These were fair points, and Rømer had to admit that not everything was accounted for. The debate had a philosophical dimension, too. Cassini and his supporters felt that a theory should explain all observations, not just some. Rømer countered that the other effects were smaller and harder to measure, but the speed of light effect was the dominant one for Io. It was a genuine scientific disagreement, conducted with the standards of evidence available at the time. Over the following decades, more evidence accumulated. In 1728, the English astronomer James Bradley made an independent observation that supported the idea of finite light speed. Bradley was studying something called stellar aberration, a slight apparent shift in the positions of stars caused by Earth's motion through space. As Earth orbits the Sun, the direction from which starlight appears to come changes slightly, much like how rain seems to slant toward you when you're running, even if it's falling straight down. By carefully measuring this aberration, Bradley could calculate the speed of light. His result was about 301,000 kilometers per second, closer to the true value than Rømer's estimate had been. Slowly, the scientific community began to accept that light had a measurable, finite speed. Descartes' instantaneous light was set aside. The universe was revealing itself to be a place where effects took time to propagate, where distance mattered, where the cosmos operated on a scale far grander and stranger than philosophers had imagined. But astronomers weren't satisfied with observations from space alone. If light truly had a finite speed, shouldn't it be possible to measure it right here on Earth in a laboratory, with carefully controlled equipment? This became the next challenge, and it would occupy some of the finest experimental minds of the 19th century. The first successful terrestrial measurement came from a French physicist named Armand Hippolyte Louis Fizeau in 1849. Fizeau's method was wonderfully clever. He sent a beam of light through the gaps between teeth on a rapidly spinning wheel. The light traveled 8 kilometers to a distant mirror and was reflected back toward the wheel. At slow rotation speeds, the returning light would be blocked by a tooth. But at precisely the right speed, the wheel would rotate just enough that the returning light would pass through the next gap, making it visible to the observer. By knowing the speed of the wheel's rotation, the distance to the mirror, and the spacing of the teeth, Fizeau could calculate how fast the light traveled. His result was 315,000 kilometers per second, remarkably close to the true value. Just a year later, another French physicist, Léon Foucault, improved on this technique by replacing the toothed wheel with rotating mirrors. This allowed for even more precise measurements and yielded a value of about 298,000 kilometers per second, even better than Fizeau's. Foucault's experiment also revealed something fascinating. When he measured the speed of light traveling through water, it was slower than in air. This was an important confirmation of the wave theory of light and contradicted some earlier ideas about how light should behave in different materials. Light wasn't just fast. Its speed changed depending on what it traveled through, slowing down in denser media. This observation would later play a crucial role in understanding refraction and the behavior of lenses and prisms. As the 19th century progressed, new technologies and more refined methods allowed scientists to measure the speed of light with increasing precision. The American physicist Albert Michelson became perhaps the most famous name associated with these measurements. In the 1880s and again in the 1920s, Michelson conducted a series of experiments using rotating mirrors and long baselines between mountaintops in California. His most famous setup involved an 8-sided rotating mirror on Mount Wilson and a plane mirror 35 kilometers away on Mount San Antonio. Light would bounce between these mirrors, and by precisely controlling the rotation speed and measuring the light's path, Michelson achieved measurements accurate to within a few kilometers per second. His work was so impressive that he became the first American to win the Nobel Prize in Physics in 1907. Michelson's 1926 measurement gave a value of 299,796 kilometers per second, incredibly close to what we use today. After James Clerk Maxwell published his groundbreaking theory of electromagnetism in the 1860s, showing that light was an electromagnetic wave, it became possible to calculate the speed of light indirectly. Maxwell's equations related the speed of light to two fundamental constants of electricity and magnetism: the permittivity and permeability of free space. By measuring these electrical and magnetic properties carefully, physicists could derive the speed of light without even using light itself. These indirect measurements agreed beautifully with the direct astronomical and terrestrial measurements, providing powerful confirmation that Maxwell's theory was correct and that light was indeed an electromagnetic phenomenon. This convergence of different methods, all pointing to the same value, was deeply satisfying to physicists. The universe was consistent. Different approaches to the same question yielded the same answer. By the mid-20th century, the development of lasers and atomic clocks had pushed measurement precision to extraordinary levels. Scientists could now measure the speed of light to within a meter per second or better. At that point, something interesting happened. The precision of the measurement exceeded the precision with which the meter itself was defined. The meter had originally been defined as 1/10,000,000th of the distance from the equator to the North Pole, but this wasn't a very practical standard for precise work. For a while, the meter was defined by a physical metal bar kept in Paris, but even that had limitations. By the 1970s, it made more sense to flip the problem around. Instead of using a defined meter to measure the speed of light, why not define the speed of light exactly and use that to define the meter? So, in 1983, by international agreement, the meter was redefined as the distance light travels in a vacuum during 1/299,792,458th of a second. This made the speed of light exactly 299,792,458 meters per second by definition. It's no longer a measured value subject to experimental error. It's a defined constant that anchors our system of measurements. So, what does this number actually mean? 299,792,458 meters per second. Let's break it down into terms that might feel more tangible. That's roughly 300,000 kilometers per second, or about 186,000 miles per second. In 1 second, light travels far enough to circle Earth's equator about 7.5 times. Think about that. In the time it takes you to say 1 Mississippi, light has lapped the planet over 7 times. If you could somehow travel at the speed of light, you could go from New York to London in about 15 thousandths of a second. From Earth to the Moon in just over 1 second. From Earth to the Sun in about 8 minutes and 20 seconds. These numbers start to feel almost surreal, because they're so far removed from our everyday experience of motion. But the speed of light isn't just about how fast something goes from point A to point B. It's woven into the fundamental fabric of how the universe works. When we look at the sun, we're not seeing it as it is now, but as it was about 8 minutes ago. The light we receive left the sun's surface 8 minutes in the past and has been journeying through space ever since. When we look at the nearest star system, Alpha Centauri, we see it as it was about 4 years ago. The light from distant galaxies took millions or even billions of years to reach us. We're literally looking back in time when we gaze at the night sky. Astronomy is a form of time travel, not in the science fiction sense of visiting the past, but in the profound sense that the universe's vast distances mean we always observe the past, never the present. The farther away something is, the further back in time we're seeing it. This has deep implications for our understanding of the cosmos. When astronomers study galaxies billions of light-years away, they're observing those galaxies as they existed billions of years ago, when the universe was younger, when stars were forming in different patterns, when the cosmic web of matter was still taking shape. We can watch the history of the universe unfold by looking at objects at different distances. The speed of light creates a natural archive of cosmic history, scattered across the sky at different distances. Every photon that reaches our telescopes carries information from the past, from places and times we can never visit in person but can nonetheless observe and study. The universe is not just vast in space, it's vast in time, and the speed of light is what links these two dimensions together. But the story of light speed took its most profound turn in the early 20th century, when a young physicist working in a patent office in Switzerland began thinking deeply about what it would mean for the speed of light to be the same for all observers, regardless of how they were moving. His name was Albert Einstein, and his insights would revolutionize physics and our understanding of reality itself. In 1905, Einstein published a paper titled On the Electrodynamics of Moving Bodies, which laid out his special theory of relativity. The core idea was deceptively simple but staggeringly radical. Einstein proposed that the laws of physics, including the speed of light, are the same for all observers moving at constant velocities relative to each other. This might not sound revolutionary at first, but consider what it means. If you're standing still and measure the speed of a beam of light, you get a certain value. If you're moving at half the speed of light and measure the same beam, you still get the same value. The speed of light doesn't add or subtract based on your motion. It's always the same, always constant, always exactly 299,792,458 meters per second. This was completely contrary to how we intuitively think about speeds. If you're on a train moving at 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour relative to the train, someone standing beside the tracks would see the ball moving at 70 kilometers per hour. Velocities add. That's common sense, and it works perfectly well for everyday speeds. But Einstein realized that light doesn't behave this way. No matter how fast you're moving, light still zips past you at the same speed. This constancy of light speed wasn't just an interesting quirk. It was a fundamental feature of the universe that required a complete rethinking of space and time. If the speed of light is constant for all observers, then space and time themselves must be flexible, must be relative, must change depending on your motion so that everyone can measure the same speed for light. One consequence of this is time dilation. If you travel at very high speeds, close to the speed of light, time passes more slowly for you than for someone who's stationary. This isn't an illusion or a trick of perception. It's real. A clock on a fast-moving spaceship actually ticks more slowly than a clock on Earth. If you left Earth on a spaceship traveling at 90% of the speed of light and came back after what felt like 10 years to you, decades or even centuries might have passed on Earth. This seems impossible, but it's been verified experimentally countless times. Particles created in cosmic ray collisions high in Earth's atmosphere should decay in microseconds. But because they're traveling close to the speed of light, time slows down for them, and they survive long enough to reach the ground and be detected. Atomic clocks flown on airplanes run slightly slower than clocks left on the ground. Astronauts on the International Space Station, traveling at about 28,000 kilometers per hour, age slightly more slowly than people on Earth. The effect is tiny at these speeds, just milliseconds over years, but it's measurable and real. Another consequence is length contraction. An object moving at high speed appears shorter in the direction of motion than it does when at rest if you could watch a spaceship zoom past you at 90% of the speed of light. It would look compressed, squashed along its direction of travel. And from the perspective of someone on that spaceship, it's the outside universe that appears contracted. Both perspectives are equally valid. There's no absolute frame of reference, no privileged viewpoint that's more correct than any other. Space and time are not fixed backdrops against which events unfold. They're dynamic, malleable, and dependent on the observer's state of motion. This was Einstein's great insight. The universe is far stranger than our everyday experience suggests, and the constancy of the speed of light is the key that unlocks this strangeness. Einstein's special relativity also gave us the most famous equation in all of science. E equals mc squared. Energy equals mass times the speed of light squared. This equation says that mass and energy are interchangeable, two forms of the same underlying thing. A small amount of mass can be converted into an enormous amount of energy because the speed of light squared is such a huge number. When you square 300,000 kilometers per second, you get 90 trillion kilometers squared per second squared, or in more standard units, about 90 quadrillion in energy terms. This is why nuclear reactions release so much energy. A tiny amount of matter, when its mass is converted to energy, produces tremendous power. The sun shines because of this equation, fusing hydrogen into helium and turning a bit of mass into the light and heat that make life on Earth possible. Nuclear power plants and atomic weapons operate on the same principle. Mass is energy. Energy is mass, and the speed of light is the conversion factor between them. But why is the speed of light the cosmic speed limit? Why can't anything go faster? The answer lies in what happens as you approach light speed. As you go faster, your mass effectively increases from the perspective of a stationary observer. The energy required to accelerate you further also increases. As you get closer and closer to the speed of light, your effective mass approaches infinity, and the energy required to push you any faster also approaches infinity. To actually reach the speed of light, you'd need infinite energy, which is impossible. Nothing with mass can reach light speed, let alone exceed it. Light itself, and other massless particles like gravitons, can travel at this speed precisely because they have no rest mass. They're born moving at light speed, and can't exist at any other velocity. This speed limit isn't just about light or particles. It's about causality, about cause and effect, about the very structure of how events relate to each other in the universe. If information or influence could travel faster than light, it would create paradoxes where effects could precede their causes. You could, in principle, send a signal into your own past and change events that already happened. This violates the logical structure of reality as we understand it. The speed of light isn't just the speed at which light travels. It's the maximum speed at which any cause can produce an effect, the rate at which influence can propagate through the universe. It defines what's possible, what regions of space and time can affect each other, and what must remain forever separate. In 1907, a few years after Einstein's special relativity paper, one of Einstein's former teachers, a mathematician named Hermann Minkowski, showed that special relativity could be understood geometrically. Minkowski proposed that we should think of space and time not as separate things, but as a unified four-dimensional structure called spacetime. In this view, an event doesn't happen at a location in space and at a moment in time separately. It happens at a point in spacetime, with 3 spatial coordinates and 1 time coordinate. The speed of light becomes a kind of conversion factor between the units of space and the units of time, linking them into a single continuum. Moving through space means you're also moving through time, and the faster you move through space, the slower you move through time, in such a way that the space-time interval between events remains constant. Minkowski's space-time picture was initially dismissed by Einstein as unnecessarily abstract, but he quickly realized its power. This geometric view of space-time became essential when Einstein extended his theory to include gravity about 10 years later. General relativity, published in 1915, showed that gravity isn't a force in the traditional sense, but rather a curvature of space-time caused by mass and energy. Massive objects like stars and planets warp the fabric of space-time around them, and other objects move along the curved paths created by this warping. Light follows these curves too. When light passes near a massive object, its path bends, an effect called gravitational lensing. This bending isn't because gravity pulls on light directly, but because space-time itself is curved, and light travels along the shortest path through that curved space. In general relativity, the speed of light remains fundamental. It's still the maximum speed for any signal or particle. But now it plays a deeper role. It defines the causal structure of the universe, determining which events can influence which other events. Every point in space-time is surrounded by what's called a light cone, a boundary defined by light traveling out from that point. Anything inside your past light cone could have affected you. Anything inside your future light cone you could potentially affect. But events outside your light cone are causally disconnected from you. They can neither influence you nor be influenced by you, because doing so would require a signal to travel faster than light. The geometry of space-time, the structure of reality itself, is shaped by the speed of light. Black holes are perhaps the most dramatic demonstration of how the speed of light structures the universe. A black hole forms when matter collapses into such a small region that its gravitational field becomes so intense that nothing, not even light, can escape. The boundary around a black hole, called the event horizon, is precisely the surface where the escape velocity equals the speed of light. Cross that boundary and you cannot come back, because doing so would require traveling faster than light, which is impossible. Inside the event horizon, all paths lead inward, toward the singularity at the center. The future direction in time becomes the inward direction in space. This is mind-bending stuff, but it all follows from the principles of relativity and the role of light speed as the ultimate limit. The speed of light also governs practical technologies in our everyday lives. Global Positioning System satellites, for example, rely on incredibly precise timing. Each satellite carries an atomic clock and broadcasts the time along with its position. Your GPS receiver picks up signals from multiple satellites and calculates your position based on how long each signal took to arrive. Because those signals travel at the speed of light, even tiny timing errors translate into significant position errors. But there's a catch. The satellites are moving quickly in orbit, so special relativity predicts their clocks should run slightly slower than clocks on the ground. At the same time, they're farther from Earth's mass, so general relativity predicts their clocks should run slightly faster. When engineers account for both effects, the general relativistic speedup is larger, and the satellite clocks end up running about 38 microseconds faster per day than ground clocks. If this weren't corrected, GPS positions would drift by kilometers in just a day or two. The fact that GPS works at all is a daily confirmation that Einstein's relativity, built on the foundation of the speed of light, accurately describes our universe. Particle accelerators also brush up against the speed limit. At facilities like the Large Hadron Collider in Switzerland, protons are accelerated to more than 99.999% of the speed of light. As they approach this limit, it takes exponentially more energy to squeeze out each additional increment of speed. The particles' masses increase dramatically in the lab's reference frame, and relativistic effects become huge. Colliding particles at these energies recreates conditions that existed fractions of a second after the Big Bang, allowing physicists to study fundamental forces and particles. But the particles never reach light speed. They can't. They just get closer and closer, with their energy climbing higher and higher, demonstrating the reality of relativistic mass increase and the inviolability of the cosmic speed limit. When we communicate with spacecraft exploring the solar system, the finite speed of light introduces unavoidable delays. Radio signals, which are just another form of light, take over 8 minutes to travel from Earth to Mars when the planets are at their closest. A conversation with astronauts on Mars would have a round-trip delay of over 16 minutes. Messages sent to the Voyager probes, now in interstellar space, take over 20 hours to arrive, and another 20 hours for a reply to come back. These delays aren't technical limitations that better technology could overcome. They're fundamental constraints imposed by the structure of spacetime and the speed at which information can propagate. No matter how powerful our transmitters become, we can't send signals faster than light. This has philosophical implications too. The universe has a horizon, a distance beyond which we can never see, no matter how long we wait or how powerful our telescopes become. Because the universe is expanding and has a finite age of about 13.8 billion years, light from extremely distant regions hasn't had time to reach us yet. And because the expansion of space itself is accelerating, driven by something called dark energy, there are galaxies so far away that their light will never reach us. They're receding faster than light can cover the distance, not because they're moving through space faster than light, but because the space between us and them is expanding at such a rate that light can't bridge the gap. There's an entire portion of the universe that we are fundamentally unable to observe, not because of technological limitations, but because of the finite speed of light and the expansion of the cosmos. The behavior of light changes when it moves through materials. In a vacuum, light travels at its maximum speed, about 300,000 kilometers per second. But in the air, it slows down very slightly, by about 90 parts per million. In water, it slows to about 3/4 of its vacuum speed. In glass, depending on the type, it might travel at 2/3 or even slower. Diamond slows light to less than half its vacuum speed. These slowdowns occur because light interacts with the atoms in the material. When light enters a medium, it doesn't actually slow down in the sense that individual photons travel slower. Instead, the electromagnetic wave is absorbed and re-emitted by atoms, and this process takes time, creating an effective slowdown. The refractive index of a material tells you how much it slows light compared to a vacuum. Scientists have even found ways to slow light to extraordinarily low speeds. By carefully manipulating the quantum properties of ultra-cold atoms, researchers have reduced light to speeds of just a few meters per second, slower than a bicycle. In some experiments, light has been brought to a complete stop, captured in a cloud of atoms, held there for a moment, and then released to continue on its way. These experiments explore the quantum nature of light and matter, and they may eventually lead to new technologies for storing and manipulating information. But they don't violate relativity. The light slows because it's interacting with matter in complex ways. In a vacuum, with no interactions, light always travels at the same universal speed. There's something deeply mysterious called quantum entanglement that seems to challenge the speed of light limit, but doesn't actually violate it. When two particles are entangled, measuring a property of one particle instantaneously determines the corresponding property of the other, no matter how far apart they are. This correlation appears to happen faster than light, leading Einstein to famously call it spooky action at a distance. But here's the key. While the correlation is instantaneous, no information is transmitted. You can't use entanglement to send a message faster than light. The results of measurements on entangled particles are random, and only when you bring the results together, at speeds limited by light, can you see the correlation. Quantum mechanics and relativity coexist. Strange as that may be, the universe remains consistent, even if it's strange in ways we're still working to understand. The speed of light raises profound questions about free will, determinism, and the nature of the present moment. If the speed of light limits how quickly one event can affect another, then for any given moment, there are vast regions of the universe that cannot yet have affected you and that you cannot yet affect. In a sense, those regions don't exist in your present. They're in your future or your past, depending on where they are and how they're moving. The present moment isn't a universal slice through time. It's different for different observers. What's happening now, somewhere far away, depends on how you're moving. This suggests that past, present, and future all exist together in the space-time continuum, a four-dimensional structure where time is just another direction, no more special than up or down. This view, called eternalism or the block universe, is deeply unsettling to many people because it seems to imply that the future already exists and that our experience of time flowing is somehow illusory. These are philosophical questions that physicists and philosophers continue to debate, questions that arise directly from taking the constancy of the speed of light seriously. Despite over a century of study, there are still mysteries surrounding the speed of light. Why does it have the value it does? Why 299,792,458 meters per second and not some other number? In our current theories, the speed of light is a fundamental constant that simply is. We can measure it, use it, build theories around it, but we can't explain why it has the particular value it does. Some physicists speculate that different universes, if they exist, might have different values for the speed of light, leading to radically different physical laws and structures. In universes where light was much slower or much faster, atoms might not form, stars might not burn, and life as we know it couldn't exist. The speed of light might be one of many constants fine-tuned to allow for complexity and life, though this idea remains speculative. There's also the question of whether the speed of light has always been constant. Most physicists believe it has, but some alternative theories suggest that the speed of light might have been different in the very early universe, or that it might vary slightly in strong gravitational fields or under extreme conditions. So far, observations of light from distant galaxies, which we're seeing as it was billions of years ago, show no evidence that the speed of light has changed over the age of the universe. Theories proposing a varying speed of light face significant challenges and haven't gained widespread acceptance, but they remind us that science is always open to new evidence and new ideas. We can never be absolutely certain that our current understanding is final. The speed of light, for now, remains a constant, but we continue to test and probe this assumption in ever more precise ways. Another puzzle involves the question of whether space itself might have some kind of structure that affects light's speed. In quantum gravity theories, some physicists propose that space-time might not be smooth at the smallest scales, but rather grainy or foamy, made of discrete units far smaller than atoms. If this were true, light of different energies might travel at slightly different speeds, with high-energy gamma rays perhaps moving marginally slower or faster than low-energy radio waves. Observations of distant gamma-ray bursts, events that release light of many different energies all at once, have been used to search for such effects. So far, no convincing evidence of energy-dependent light speed has been found. Light behaves as if space-time is smooth, at least down to scales far smaller than we can currently probe directly. But the search continues, because finding such an effect would revolutionize our understanding of gravity and quantum mechanics. The speed of light also plays a role in one of the greatest unsolved problems in physics: the quest to unify general relativity and quantum mechanics into a single theory of quantum gravity. These two pillars of modern physics are each spectacularly successful in their own domains, but they seem fundamentally incompatible when combined. General relativity describes gravity as the curvature of smooth, continuous spacetime, with the speed of light as a fundamental feature of that geometry. Quantum mechanics describes the world of particles and fields as discrete, probabilistic, and subject to uncertainty principles. Bringing them together is extraordinarily difficult, and the speed of light sits at the heart of this difficulty. Any successful theory of quantum gravity will have to respect the role of light speed as both a geometric feature of space-time and a limiting velocity for particles and information. String theory, loop quantum gravity, and other approaches all grapple with this challenge in different ways, but a complete tested theory remains elusive. The speed of light defines our cosmic neighborhood in a very real sense. The observable universe, the part we can in principle see, has a radius of about 46 billion light-years. This is larger than 13.8 billion light-years, the age of the universe, because the universe has been expanding during the time light has been traveling. Light from the most distant visible galaxies has been journeying toward us for almost the entire history of the cosmos, and during that time, both we and those galaxies have been carried apart by the expansion of space. But there's a limit. Beyond a certain distance, objects are receding so quickly due to the expansion that their light will never reach us. The speed of light, combined with the expansion of space, creates a boundary to what we can observe. Beyond that horizon, there may be more universe, perhaps infinitely more. But it's forever beyond our reach. We're confined to our cosmic bubble, isolated by the same speed limit that structures time and causality within our observable region. The speed of light is also crucial in understanding the fate of the universe. The expansion of the universe is accelerating, driven by dark energy, a mysterious component that makes up about 70% of the universe's energy content. As time goes on, distant galaxies will recede faster and faster. Eventually, all galaxies outside our local group will be moving away faster than light can travel through the expanding space. They'll fade from view, their light stretched to undetectable wavelengths by the expansion. In the far future, many trillions of years from now, an observer in the Milky Way might look out and see only our local cluster of nearby galaxies, with the rest of the universe having disappeared beyond the horizon. The light from those distant galaxies will have redshifted so much that it becomes essentially unobservable. The observable universe will shrink, not because anything is destroyed, but because the expansion of space, combined with the finite speed of light, carries distant regions beyond our ability to see them. There's a certain poetry to all of this. The speed of light, a simple number describing how fast something travels, turns out to be one of the most profound features of existence. It links space and time into a unified space-time. It sets the cosmic speed limit, ensuring that cause precedes effect and preventing paradoxes. It determines what regions of the universe can interact and which must remain isolated. It makes the universe's history visible, letting us look back in time by looking outward in space. It's encoded into the structure of matter and energy through Einstein's equation, explaining where the power of the sun comes from and why nuclear reactions release such tremendous energy. And it shapes the fate of the cosmos, determining what we can see and what will forever remain beyond our horizon. For all our technological sophistication and scientific understanding, we live in a universe constrained by this speed. No matter how fast we build our spaceships, we'll never cross the galaxy in minutes or years. Interstellar travel, if it's ever achieved, will be a slow process measured in decades or centuries, at least from the perspective of those left behind. Our descendants might reach distant stars someday, but they'll be traveling forward into a future that we can only imagine. The stars are far away, and the speed of light reminds us of that distance in the most fundamental way. There's something humbling and awe-inspiring about this. We've measured the speed of light, calculated it, defined our units by it, built technologies that depend on it, and woven it into our deepest theories about the nature of reality. Yet we can't exceed it. We can't go around it. We can't cheat it. It's built into the rules, a cosmic speed limit that we must accept. And in accepting it, we come to understand the universe a little better. We see that space and time are not the stage on which events play out, but rather participants in the drama, flexible and interconnected, shaped by matter and energy, constraining what's possible and what's not. Light itself is extraordinary. It's massless, tireless, traveling at the maximum possible speed from the moment it's created until it's absorbed. A photon emitted from a distant star 13 billion years ago has been rushing through space ever since, covering unimaginable distances, passing through vast voids and clouds of gas, untouched by time in its own reference frame, until finally it enters your eye or your telescope tonight. To that photon, if we could imagine its perspective, no time has passed at all. At the speed of light, time dilation is complete. The photon's journey is instantaneous from its point of view, even though billions of years have elapsed in the outside universe. It's born and dies in the same moment, from its own frame of reference, yet its path connects events separated by cosmic distances and time spans. There's a strange beauty in that paradox. As you drift off to sleep tonight, consider the light around you, the glow of a screen, the moonlight through a window, the distant stars barely visible above the horizon. Every bit of that light has traveled to reach you, carrying energy and information across space, arriving at your eyes at a speed that's been constant throughout the universe's history. The photons hitting your retina might have been created just moments ago in a light bulb filament, or they might have journeyed for thousands of years from a distant star. But they all arrive traveling at the same speed, the speed that defines our universe's structure, the speed that makes time and space what they are, the speed that sets the limits of what we can know and experience. The speed of light is more than just a number. It's a window into the deep architecture of reality. It tells us that the universe has rules, patterns, limits. It tells us that distances matter, that time isn't absolute, that past and future are woven into the geometry of space-time. It tells us that we're part of a cosmos that's stranger and more wonderful than common sense suggests. A cosmos that rewards careful observation and deep thought with insights that reshape our entire worldview. From Rømer, watching Jupiter's moons, to Einstein reimagining space and time. From Fizeau's spinning wheel to modern GPS satellites compensating for relativistic effects, the story of the speed of light is a story of human curiosity and ingenuity, of asking questions and following where the answers lead, even when those answers challenge everything we thought we knew. And so, we come to the end of tonight's journey through the cosmos of light and speed, through centuries of discovery and layers of meaning. You've traveled from ancient debates about whether light was instantaneous, through the first measurements using eclipses and spinning wheels, into Einstein's revolutionary insights about space and time, and out to the horizons of the observable universe. The speed of light has been your guide, a constant companion through this exploration, always present, always the same, connecting every part of the story. If these gentle explorations of science and wonder help you find peace at the end of the day, consider liking this video and subscribing to the channel. It helps others discover these stories too, and it lets me know that these journeys matter to you. As you close your eyes and let sleep approach, remember that you're made of atoms forged in ancient stars, held together by forces that respect the same speed limit as light itself. The universe is vast beyond imagining, but it's governed by principles we can understand, patterns we can measure, constants, like the speed of light that remain true across billions of years and trillions of miles. There's comfort in that consistency, in knowing that the same light that warmed primordial planets now illuminates your path, that the same laws that shape galaxies also determine how quickly signals travel from your brain to your fingertips. You're part of this cosmos, subject to its rules, connected by light to everything else that exists. Sleep well tonight, knowing that the universe is a place of profound order beneath its apparent chaos, a place where light travels at exactly the speed it should, where time and space dance together in elegant mathematical harmony, where the distant past is visible in the night sky, and where the future awaits, always moving forward, never faster than light will allow. Good night.